Okay, good morning. I wanted to discuss average atomic weight. Sometimes it is called the average atomic mass, whatever you prefer. I kind of go back and forth. Um, but when we're talking about the average atomic weight, by definition, a weighted average of all of the masses of the naturally occurring isotopes expressed in atomic mass units. So this is the number I'm talking about on the periodic table of elements. So for this lesson, you will need a calculator and your periodic table of elements. You can use the one on Bright Thinker, or you can have your own. I quite often like to have a hard copy in my hand when I'm doing these, but you can just pull one up in a different tab off of Bright Thinker. So first of all, just a reminder, elements, all the elements on the periodic table have two or more isotopes. And again, isotopes are atoms of the same element with a different number of neutrons or in a different atomic weight or in a different atomic mass. So the way this average atomic weight in AMUs is calculated is it is a weighted average. So it is very, very similar to the way a teacher might weight their grades. So a quick example here. So I'm just going to look at student B. So if we were to calculate their average grade, okay, of all of these tests, you would just add each of these together and then divide by 5, and that would give you just the average. The weighted average places more importance on certain items or certain tests or certain assignments. So let's say, for instance, our teacher wants to go ahead and weight our exam A 40%. So that means that of all their tests, or sorry, not exam A, exam 5 is worth 40%. Let's say they want to weight exam 4 30%. So let's say instead of them having a final, the teacher is going to weight exams 4 and 5, 30 and 40%, meaning they're placing more importance on those two tests. And let's say the teacher wants to weight everything else 10%. So a weighted average is placing a certain importance on a specific grade or on something. So if I take my calculator and if I will do 76 times 10%, that's going to be 7.6. 88 times 10% is 8.8. 90 times 10% is 9. 81 times 0.20 is 24.3. And 72 times 0.40 is going to be 28.8. And I'm going to add all of those together to get my weighted average. So this per student's weighted average would actually be 78.5%. So if this teacher weighted their tests differently, that average is going to be a little bit lower than the average if we were to add them all together and divide by 5. So this is a great example of how our atomic weight is actually calculated. So again, I'll use carbon as an example. So carbon has 3 isotopes. So we have carbon 12, we have carbon 13, and we have carbon 14. So each of these isotopes of carbon have a different weight or a different mass because they each have a different number of neutrons. They also have a different percent abundance. Percent abundance is how often they are found in nature. So how often are they found in compounds or in molecules? So Carbon-12 has a mass of 12.000 AMUs. Carbon-13 has a mass of 13.00335. Carbon-14 has a mass of 14.00324. Of course, carbon-14 is going to have a bigger mass because it has more neutrons. Now, carbon-12 has a percent abundance of 98.93%. Carbon-13 has a percent abundance of 1.07%, and carbon-14, it is found so rarely that there is not a percent abundance. So when it comes to our average atomic weight on the periodic table, it is going to be closest to carbon-12's weight because carbon-12 has a percent abundance of 98.3%. So that means we're placing more importance on carbon-12's weight. However, we have to also think about the weight or the mass of carbon-13. So they calculate it like a weighted average, just like I did before. So I would do 12 times 0.9893, and that's going to give me 11.8716. And if I was to do 13.00335 times 0.1017, that is going to give me a number of 0.1314. If I add both of those together, my average atomic weight is 12.011, what matches here. So that average atomic weight on the periodic table is going to be closest to carbon-12 because it has a bigger percent abundance. Okay, so that's what a weighted average is. So let's look at calculating it. So like I showed you before in the previous slide, percent abundance, you need the percent abundance of each isotope, and it's going to be in decimal form. So carbon-12 had a 98.93%. So before I did a calculation, I had to move the decimal over 2 places. It's like you're dividing by 100. So in decimal form, it would be 0.9893, and carbon-13 had a percent abundance of 1.07, so I had to move that decimal over twice, 0.0107%. You need to know the mass of each element, each isotope's element, or each element's isotope, I should say. And it's pretty simple. Take the mass of isotope 1, multiply it by its percent abundance in decimal form. Mass of isotope 2, multiply by its percent abundance in decimal form. And if you have a third isotope, you would do the same thing, and then you're just going to add them all together. It may tell you what the element is, the problem may not. So this is when you would need your periodic table. So let me give you a quick example here. So a certain element is a soft silvery white metal that has 2 common isotopes. The first isotope has a mass of 85 AMUs. The second has a mass of 87. If the abundance of the first isotope is 72.2 and the second is 27.8, what is the average atomic mass or weight, and what's the element? So I'm going to start, I like to do all my math first. 85 times 0.722. Again, I have to move my decimal over. And 87 times, again, move my decimal over, 0.278. Now I'm going to grab my calculator. I'm going to do 85 times 0.722. 85 times 0.722 is going to give me 61.37. 87 times 0.278 will give me 24.186. I'm going to add those together. So this element has an average atomic weight of 85.556 AMUs. Now, due to significant figures, it's going to be pretty close to the periodic table, but it might not be perfect. So I'm going to scroll over, let's see, 85. Here we go. What was our, let me double check, 85.556, 85 points. So I can't see it. So that is going to be closest to rubidium. Again, due to significant figures, it might not be exactly perfect, but it'll be pretty darn close. Okay, let's do one more. And then your job is going to be to calculate this problem, solve this problem, and solve this problem as well. And then upload your work into Bright Thinker. You can either do it on your computer with their stylus, or you can do it on a sheet of paper, take a picture, and upload that. Okay, so let me see how much time we got going on here. Okay, let's give this another try. Okay, 2 naturally occurring isotopes of a certain element needed for the summer months. The first isotope has a mass of 34.969 AMUs, and its percent abundance is 75.53. Second isotope has a mass of 36.966 AMUs with a percent abundance of 24.47. Again, I like to write it all out, and I do expect for you to show your work. 0.969 times 0.7553 give us 26.41. 36.966 times 0.2447 is equal to 9.045. I'm going to add those together. Plus 9.045 is going to give us 35.455 AMUs. So then let's go back to my periodic table. 35. Let's see. Periodic table, 35.455. And my element is going to be chlorine. Okay, that's how you work your average atomic weight problems. Again, you are going to have this problem. I will make this problem A. You can work it on a document, or you can work it on a PowerPoint. You could take your snipping tool and put it in the submission area. We'll make this problem number B, letter B, sorry. Same thing, you can work it on a document with a stylus. You can use your snipping tool, put it in the submission area. You could do both of these on one document, upload the document. You could work both of these on a sheet of paper, take a picture, and upload it. Any of those are options. Please show your work like I did, and have a great day. Thanks a lot.